In 1998, astronomers made the most shocking discovery in the universe. The universe isn't just expanding, it's accelerating, as if an invisible force is pushing all galaxies apart. This discovery vindicated what Einstein called his greatest mistake, the cosmological constant. But what is this mysterious force? To answer this question, we need to go back before 1998. At the beginning of the 20th century, what we knew about the universe was very simple. In Newton's universe, everything was predictable. Planetary motions, comet orbits, tidal forces. Mathematics worked perfectly. Then Einstein came and changed everything. General relativity theory defined gravity as the curvature of space-time. It was revolutionary. But Einstein's equations contained a problem. They didn't give a static universe. Einstein's equations said the universe must either expand or contract. But in 1915, everyone believed the universe was fixed, unchanging. Einstein added a new term to his equations to solve this problem, the cosmological constant, lambda. Lambda was energy density contained in space itself. It behaved like anti-gravity, trying to expand space. Einstein adjusted lambda so it balanced with gravity's attractive force. Thus he achieved a static universe. It was mathematically elegant, but philosophically motivated. But in 1929, Edwin Hubble made the observation that changed everything. Using the 100-inch Hooker telescope at Mount Wilson, he observed that distant galaxies were moving away from us. And the more distant the galaxy, the faster it was receding. Hubble's law, distance is directly proportional to velocity. This meant the universe was expanding. The Big Bang theory was born. The universe had started from a single point, expanding to reach its current state. Einstein's static universe assumption was wrong. The cosmos had a history, a beginning, an evolution. Einstein called the cosmological constant the greatest mistake of my life. He removed lambda from his equations. If the universe was expanding, this expansion should slow down due to gravity, because all matter attracts each other. This seemed obvious to everyone. For 70 years, this view dominated cosmology. The universe was expanding but decelerating. Gravity was gradually winning its battle against the initial explosive force of the Big Bang. The key question was, how much was it slowing? Would gravity eventually stop expansion entirely, leading to a big crunch? Or would expansion continue forever, leading to a cold, empty future? To answer this question, astronomers needed to measure how the universe's expansion rate changed with time. This required looking at very distant galaxies, very distant times. Since light speed is finite, seeing far means seeing the past. The challenge was finding reliable distance indicators. By the 1990s, technology had developed sufficiently. CCD cameras could capture faint light with unprecedented sensitivity. Large telescopes like Keck and the Hubble Space Telescope could observe the most distant objects. Powerful computers could analyze vast datasets. 2 research groups undertook this ambitious mission. Saul Perlmutter's Supernova Cosmology Project at Lawrence Berkeley National Laboratory. Brian Schmidt's High-Z Supernova Search Team, an international collaboration centered in Australia. Both had the same goal, but worked independently. Both groups used the same method. Type 1a supernovae. These stellar explosions are special because they're remarkably uniform. A white dwarf star in a binary system pulls matter from its companion. When the white dwarf reaches 1.4 solar masses, the Chandrasekhar limit, it undergoes runaway nuclear fusion and explodes. The physics of this explosion is well understood. Each Type 1a supernova releases roughly the same energy, making them standard candles, objects of known intrinsic brightness. By comparing how bright they appear with how bright they actually are, astronomers can calculate their distance with remarkable precision. But you can also analyze the supernova's spectrum. The light is redshifted by cosmic expansion, wavelength stretched as the universe grows. By measuring this redshift, you determine how fast the supernova's host galaxy is receding. Combined with distance, this gives you the expansion rate at different cosmic epochs. The search process was painstakingly systematic. Teams would photograph the same patches of sky repeatedly, looking for new points of light that hadn't been there before. Potential supernovae required spectroscopic follow-up to confirm their type and measure redshift. The entire process, from discovery to analysis, could take months. Between 1995 and 1998, both groups observed dozens of high redshift supernovae. The data was carefully analyzed, systematics rigorously tested. They checked for dust extinction, evolution effects, selection biases, gravitational lensing. Every possible source of error was scrutinized. The results were completely unexpected. Distant supernovae appeared dimmer than predicted by a decelerating universe model. Much dimmer. The immediate reaction was that something was wrong. Perhaps dust in intergalactic space was absorbing light, or distant supernovae were intrinsically fainter than nearby ones.
But every systematic check pointed to the same stunning conclusion. These supernovae were really farther away than expected in a decelerating universe. The only explanation: by the time their light reached us, space had expanded more than anticipated. The universe's expansion was accelerating. This was revolutionary. For the expansion to accelerate, there had to be a repulsive force overwhelming gravity's attractive pull. But what could provide such a force? No known form of matter or energy could explain this cosmic acceleration.
The name dark energy was coined by astrophysicist Michael Turner. Dark because it doesn't interact with electromagnetic radiation. Energy because it seems to be a property of space itself, contributing to the universe's energy density. But what is dark energy? We don't know. The simplest possibility is Einstein's cosmological constant, unchanging throughout space and time. This represents the energy of empty space itself. Quantum mechanics suggests empty space bubbles with virtual particles constantly appearing and annihilating. Perhaps this is dark energy. But calculations give an answer 120 times too large, the biggest disagreement in physics. Another possibility is quintessence, dynamic dark energy that changes over time. If it strengthens, we get the Big Rip. Dark energy tears apart galaxies, planets, atoms. If it weakens, the universe could recollapse. Maybe we're wrong about gravity. Einstein's theory works locally, but might fail on cosmic scales. What appears to be dark energy could be space-time behaving differently than expected. String theory suggests our universe is one of countless universes with different dark energy values. We exist where the value allows structure formation, the anthropic principle. Several major projects are testing these ideas. The Dark Energy Survey, Euclid mission, Nancy Grace Roman Space Telescope will measure how dark energy behaves over cosmic time, determining whether it's constant or evolving. The 2011 Nobel Prize was awarded to Perlmutter, Schmidt, and Rees. Their discovery fundamentally changed cosmology. For billions of years, matter dominated. About 5 billion years ago, dark energy took over. We're now in the dark energy era of accelerated expansion. Star formation is declining as expansion separates gas reservoirs. Eventually, the universe will contain only dead remnants. But understanding dark energy could unlock new physics, perhaps faster than light travel. Meanwhile, the universe continues accelerating. In our local neighborhood, gravity wins. Andromeda will collide with the Milky Way. But on larger scales, dark energy reigns supreme. Galaxy clusters become isolated islands in an expanding ocean. As Carl Sagan said, science is a candle in the dark. The 1998 discovery lit one of physics' brightest candles while revealing vast darkness in our knowledge. The universe whispered its secret in 1998. I am accelerating. Now it's our turn to understand the invisible force reshaping cosmos itself. In seeking that understanding, we continue humanity's greatest adventure. These experiments will measure dark energy's equation of state, how its pressure relates to its energy density. If dark energy is Einstein's cosmological constant, this relationship is fixed. If it's quintessence, the relationship evolves with time. The 2011 Nobel Prize in Physics was awarded to Perlmutter, Schmidt, and Rees for their discovery. It fundamentally changed our view of cosmic evolution. For billions of years after the Big Bang, matter and radiation dominated. Gravity pulled matter together to form the first stars and galaxies. But about 5 billion years ago, dark energy took over. Since then, we've been in the dark energy era, accelerated expansion that will likely continue forever. This has profound implications. Star formation is declining as cosmic expansion separates gas reservoirs, yet the discovery opened new frontiers. Understanding dark energy could unlock new physics, perhaps faster than light travel through space-time engineering. If we learn to manipulate space's energy, we might achieve remarkable technologies. Meanwhile, the universe continues accelerating. Every second, space between distant galaxies grows larger. The cosmic horizon recedes as galaxies disappear beyond our reach. In our local neighborhood, gravity still dominates. Andromeda will collide with the Milky Way in 4.5 billion years. But on larger scales, dark energy reigns supreme. Galaxy clusters become isolated islands in an ever-expanding ocean. The universe becomes lonelier, emptier, yet also larger and more magnificent in scope. As Carl Sagan said, science is a candle in the dark. The 1998 discovery lit one of physics' brightest candles. But it also revealed the vast darkness of our ignorance about the universe's fundamental nature. That darkness isn't cause for despair, it's invitation. Every great discovery reveals new mysteries while solving old ones. Dark energy represents our time's greatest mystery, but also the greatest opportunity for breakthrough discovery. The universe whispered its secret in 1998, I am accelerating. Now it's our turn to decode what that means, to understand the invisible force reshaping the cosmos. In seeking that understanding, we continue humanity's greatest adventure, the quest to comprehend our cosmic home. Then Einstein came and changed everything.
General relativity theory defined gravity as the curvature of spacetime. It was revolutionary, but Einstein's equations contained a problem. They didn't give a static universe. Einstein's equations said the universe must either expand or contract. But in 1915, everyone believed the universe was fixed, unchanging. Einstein added a new term to his equations to solve this problem: the cosmological constant, lambda.
Lambda was energy density contained in space itself. It behaved like anti-gravity. Trying to expand space, Einstein adjusted lambda so it balanced with gravity's attractive force. Thus he achieved a static universe. But in 1929, Edwin Hubble made the observation that changed everything. Distant galaxies were moving away from us, and the more distant the galaxy, the faster it was receding. Hubble's law: distance is directly proportional to velocity. This meant the universe was expanding. The Big Bang Theory was born. The universe had started from a single point, expanding to reach its current state. Einstein's static universe assumption was wrong. Einstein called the cosmological constant the greatest mistake of my life. He removed lambda from his equations. If the universe was expanding, this expansion should slow down due to gravity, because all matter attracts each other. For 70 years, this view was valid. The universe was expanding but slowing down. The question was, how much was it slowing? If it slowed enough, expansion would stop, and the universe would begin contracting. Big crunch. If it expanded fast enough, it would expand forever. Cold death. To answer this question, we needed to measure how the universe's expansion rate changed with time. This required looking at very distant galaxies, very distant times. Since light speed is finite, seeing far means seeing the past. By the 1990s, technology had developed sufficiently. CCD cameras, large telescopes, powerful computers. 2 research groups undertook this mission: Saul Perlmutter's Supernova Cosmology project at Berkeley, Ryan Schmidt's High-Z Supernova Search Team in Australia. Both groups used the same method: Type 1a supernova. These supernovae are very special. They always explode the same way. A white dwarf star pulls matter from a companion star in a binary system. When it reaches the Chandrasekhar limit, it explodes. Each explosion is nearly the same brightness. That's why they're used as standard candles. Standard candle means you know the true brightness. If you measure the observed brightness, you can calculate the distance. If it looks dim, it's far. If it looks bright, it's near. It's that simple. But you can also take the supernova spectrum. By measuring redshift, you can find how fast the galaxy is receding from us. Thus you get both distance and velocity. You can draw a Hubble diagram. By comparing supernovae at different distances, you could see how the universe's expansion rate changed over time. The plan was perfect. Theoretical predictions were clear. The universe should be slowing down. Both groups observed dozens of supernovae between 19... They used the Hubble Space Telescope, Keck telescopes, the 4-meter telescope at Cerro Tololo, the world's largest telescopes. Data was collected, carefully analyzed. The results were completely unexpected. Distant supernovae appeared dimmer than expected, much dimmer. What did this mean? First thoughts: maybe there's dust in space, absorbing light. Maybe distant supernovae are different. Maybe there's systematic error in calculations. Every possible error source was checked individually. Intergalactic dust? Very little. Supernova evolution? Accounted for. Gravitational lensing? Negligible. But every check gave the same result. Distant supernovae were really dimmer than expected. The only explanation: these supernovae were really farther than expected. Because by the time their light reached us, space had expanded more than anticipated. This meant the universe's expansion was accelerating, not slowing down, accelerating. In 1998, both groups announced the same result: Perlmutter at Lawrence Berkeley National Laboratory, Schmidt at Australian National University. The physics world was shocked, because this shouldn't have been possible. All matter in the universe attracts each other. Dark matter also attracts. Radiation also slows expansion. What force could accelerate expansion? No known force could do this. Answer: dark energy. Einstein's discarded cosmological constant was returning, but this time differently. Lambda might not be a constant number now. It could be a variable, dynamic energy field. The name dark energy was proposed by astrophysicist Michael Turner. Dark because it's invisible, doesn't interact with electromagnetic radiation. Energy because it appears to be stored in space itself. But what is dark energy really? We still don't know. The simplest explanation is vacuum energy. According to quantum mechanics, empty space isn't really empty, due to Heisenberg's uncertainty principle. Virtual particle pairs constantly appear, disappear shortly after. These quantum fluctuations have energy. This energy is the same density at every point in space. As space expands, total vacuum energy increases, because more space means more energy. This is very different behavior from normal energy, but the calculations are horribly wrong. Quantum field theory predicts vacuum energy density 120 times greater than observed dark energy density. This is the largest discrepancy known in physics, the cosmological constant problem. Other theories exist too. Quintessence. Dynamic scalar field theory. This field slowly changes over time, losing potential energy. K-essence. Phantom energy. Chameleon fields. Dozens of variants exist. Or maybe the problem is in Einstein's theory. Maybe general relativity is wrong at large scales. FR gravity. Scalar tensor theories. Kaluza-Klein models. Brand-world scenarios. Dark energy could be an illusion of modified gravity. String theory offers another possibility. There could be many stable vacuum states. String landscape. Our universe is in one of these states. Anthropic principle. Only universes where dark energy has life-compatible values can develop observers. Or the holographic principle. The universe might actually be a hologram encoded on a surface. Emergent spacetime. Entropic gravity. Dark energy could be a result of holographic encoding. Which theory is correct? We don't know yet. We can't directly measure dark energy. We can only see its effects. The universe's expansion history. Large-scale structure formation. Cosmic microwave background anisotropies. These effects give a consistent picture. WMEP and Planck satellite data. Supernova surveys. Baryon acoustic oscillations. All give the same cosmic pie chart. About 68% of the universe is dark energy. 27% is dark matter. 5% is ordinary matter. And dark energy continues to dominate. 13.8 billion years ago, immediately after the Big Bang, radiation was dominant. Then the matter-dominated era. But 5 billion years ago, the dark energy-dominated era began. Since then, the universe's expansion has been accelerating. The Hubble constant is increasing. And this trend will continue increasing. Because while dark energy density remains constant, matter density decreases through dilution. Let's consider future scenarios. If dark energy is a cosmological constant, the universe will expand exponentially forever. Galaxies will move away from each other. We won't see any galaxy outside the local group. Star formation will end. The universe will cool. Heat death. But if phantom dark energy exists, the situation is much more dramatic. Wei-Joule-9 Tifo-Nice-1 equation of state. Dark energy will gradually strengthen. Big Rip scenario. First galaxy clusters will disperse, then galaxies, then stellar systems, then molecular bonds, finally atomic nuclei. Big Rip timeline, 22 billion years from now, Milky Way and Andromeda separate. 60 million years before that, the solar system disintegrates. 30 minutes before, Earth is shredded. In the final 10-12 seconds, atomic nuclei are torn apart. Or the opposite could happen. Quintessence models. Dark energy decreases over time. The universe becomes matter-dominated again, then recollapse, Big Crunch. Endless series of Big Bang, expansion, contraction, Big Crunch, or turnaround scenario. Dark energy reaches a certain minimum value, stays constant. The universe becomes asymptotically static, neither full expansion nor full contraction, eternal equilibrium. Perhaps the most exciting scenario, dark energy engineering. Future Type 3 civilizations could manipulate dark energy. Space-time metric manipulation, Alcubierre drive, traversable wormholes, closed time-like curves. Controlling negative energy density could make faster-than-light travel possible. Parallel universe access, time travel, reality manipulation. But these are currently pure speculation. The 2011 Nobel Physics Prize was awarded to Saul Perlmutter, Brian Schmidt, Adam Rees for discovery of the accelerating expansion of the universe through observations of distant supernovae, the greatest cosmological discovery of the 20th century. This discovery humbled physicists. It showed we don't know 95% of the universe. Dark matter, dark energy. Maybe the standard model of particle physics is inadequate. Maybe general relativity is incomplete. Maybe we're misunderstanding space-time's fundamental nature. Dark Energy Survey, Euclid Satellite, Vera Rubin Observatory, Nancy Grace Roman Space Telescope. Future projects will try to measure dark energy's equation of state. Is the W parameter equal to -1, or different? If W-1, cosmological constant. If W-Ni -1, dynamical dark energy. If W1-1, phantom energy. Each result will bring different physics implications. As Carl Sagan said, science is a candle in the dark. The 1998 discovery was one of modern science's brightest candles, but it also revealed the deepest darkness. Because understanding dark energy means understanding the universe. We'll learn new things about fundamental physics, space-time nature, reality structure. Maybe we'll discover completely new laws. The 1998 discovery showed us. The universe is still full of surprises. The distinction between known unknowns and unknown unknowns. Everything we thought we knew is just the tip of the iceberg of much deeper truths. And maybe the biggest lesson, science never ends. Every answer opens new questions.
Dark energy is the 21st century's greatest scientific challenge, but also its greatest opportunity. Now look at the sky. Even the empty space between those stars has energy. Invisible, unfelt, but there. The invisible force determining the universe's destiny. And you're part of this universe too. You're both reader and character of this mysterious story. Maybe in the future you'll be the ones to solve dark energy's secret. In 1998, the universe whispered its greatest secret to us. I am accelerating. Now it's our turn to decode the meaning of this whisper. The universe waits. Dark energy waits. And this waiting might be science's most thrilling adventure, because every great discovery changes our perception of reality, and dark energy might be the key to ultimate reality.